So my previous algorithm, I did every 6 by 6 square, and whatever pattern was in there gets a certain score, and I did machine learning on the patterns. Not a neural network at the time. And this time I'm using a neural network. Now, International Checkers was, I think, my third game I ever wrote. Well, fourth, right? I started with Othello, and then I did Micro, and then Mini Shogi, and then International Checkers, if I remember correctly. 22 to 31, 31 to 42. And that's the only move, and we're down to 8 pieces. Let's play it down to 6 pieces just to make sure I can get it to a position where it's in the table. But 7, let's see how many end games on 7 pieces there are. So we got 50 cells on the board. Choose, oh, I searched it at one point. So 50, choose 7 for where all the pieces are, and each one of those pieces could be one of 4 things. So 4 to the power of 7. And we get 1.6 trillion, which does not fit in memory. It might fit on your disk, but not in memory, right? Which is not very valuable because obviously in the middle of a search, to scan your disk would take way too long, right? Right. I don't know. Maybe I'll compute it and see how we can make use of it during the search. I mean, the best you could probably do if it's sitting on your disk is that you reach a position with 7 pieces and then you go look it up. But by the time you're up to 7, usually you can search all the way to the end anyway, right? So I don't know if it would be so valuable to have. Another thing we could do is see if you're down to 7 pieces, but there's no kings on the board. Then you have 50 choose 7 times 2 to the 7. Let's see what we got here. 12. Oh, that would definitely fit in your memory. But the problem is, how do you compute these if you don't know the value of positions with kings, right? Because those without tend to become those with, right? I guess you can compute the whole table and then store only these guys. I might think about that. Yeah. Because most of the interesting positions are not going to have kings on the board, right? So that might be worthwhile to compute. Yeah, I will think about that. What did we do here? And for some reason that's already solved. My guess is that there's an exchange that's going to happen in a couple of moves. I don't think this guy's program has an endgame table base, just judging by how much memory it's using and the size of the program. 15, 24, and we're down to, okay, that's why it solved it. Okay, let's get out of here so I can show you some of the features. So let me show you how big the endgame table base for this program is. So that file right there, Checkers Endgame 6, that file is where we store the values of all of the positions with 6 or fewer pieces. Let's have a brief look at the neural network involved. So we have these giant arrays, right? 2 by 2 by 50. We have 128 hidden neurons in the network. So what does that mean? So basically, if I were to draw this out, we have this checkers board, which is basically a 200 dimension array, right? Of ones and zeros, 200 bits to represent the board. So you got 200 input neurons that are either 0 or 1, right? And then you have 128 hidden neurons. I chose 128 because of how computer memory works. It makes it a whole lot faster than if you had a non-round number. Now these guys all go into each neuron with a certain weight. And then there's an activation function, right? So you take a weighted average based on these weights, and then you have to squash it, right? And so on and so forth. And then this is the output neuron. So this is what tells us that, hey, we're at a plus 0.2, we're at a negative 0.3 based on how much we're winning and losing. And then you got other weights here. And the goal of the machine learning is to figure out what's the best number for these weights, right? And to learn those weights. So you got these giant arrays, right? And to learn those weights, TCO stands for temporal cohesion learning, by the way. There's an algorithm for how much you adjust those weights. To learn those weights, you have the computer play against itself. And it says, wow, at this position, my best move takes it to that other position. That position currently is worth whatever, and so this position ought to be worth that much. And you play trillions upon trillions of... That's where the 10,000 hours comes from, right? You run the program for actually more like tens of thousands of hours now. Some of the programs that I've been running, right? Anyway... So I hope to compete at the Computer Olympiad in checkers next year, hopefully in person, because we couldn't coordinate it remotely this year.